So under this
So this
heading,
is SHO.
no, HTML will start later on. Not now. So SHM requires some more ideas. So SHM is like a amalgamation of all chapters in physics. So it is good to study as it as possible. So now we have the properties of matter, and under this heading we have three topics to be learned. The first will be the elasticity. Second will be like viscosity. And third will be surface tension. So in a way, we will also start the some basic of fluid dynamics. So you guys may start reading the S.C. Verma book for fluid dynamics. Although I will teach that separately, and that is quite extensive topic. But you just need to know the basic familiarity with the Pascal's law and Archimedes principle. So if you read, then you will have the some fair idea that will help you in learning the B and C part uh, with some ease. Otherwise, I will introduce you the underlying concept which is from the other chapter. Now, elasticity just need two things. One is the Newton's laws of motion, and other is the work energy power. With these two things, we can actually deal with the entire chapter of elasticity. So we know that whenever we apply force on a body, so when we apply force on a body, then there are two possibilities, or two types of action which can be possible with the body. One is it may accelerate, or it may not accelerate. But whether it is accelerating or non-accelerating, the thing which is always happens is the deformation. Now the deformation is not always significant, which you can visualize. So deformation is the sometimes it's an insignificant part which we don't see. But these deformations, or you can say the so-called wear and tear of the body happens because of the continuous deformation and recovery process of the rigid bodies. So when you're driving a car and you apply brake, then you may not believe that okay the car might have been stopped, but in the process of stopping the car, there are various segments of the car which has undergone the deformation. The one thing which always undergoes deformation is of course the part which holds the pressure of the load of the vehicle, the axle, the mounting, and the body as a whole. So deformation is an integral part of any rigid body. We cannot avoid deformation, but there must be some way to study about it. Okay. So we come to know the elasticity in a different way. Here we study elasticity as a impact created by the force. So we'll first of all study the elasticity. So what is elasticity? How we define it? Anyone any idea what is elasticity? So I think elasticity as a word you must have heard. You know what is elasticity?
Yes, sir. So that kinetic energy, elastic energy, perfectly.
Hmm?
So
Yeah. So
perfectly elastic collision and
yes. So what have we learned there in the perfectly elastic collision.
The kinetic energy gets exchanged between the two collisions.
Okay. So elasticity refers to the property of a body by virtue of which it can regain its original shape, size, or dimension upon the removal of the deforming force. So any body subjected to force will deform, but that is not elasticity. Elasticity is that ability to recover the deformation which you underwent while the force was applied to you. So if you can go back to your original dimension, if the force is removed, then that will measure the elastic property. So the definition is it is the so once the force is removed, then how up to what extent you regain the original shape size dimension, that defines the elasticity. So elasticity is the ability to regain the original shape, size, or dimension. So now you may think that which objects are more elastic. Okay. So if I ask you which one is more elastic, the steel wire or the rubber band, what is it? Which one is more elastic?
Rubber band.
Now this is a very general intuition about the elasticity because that is how you have perceived. But the idea is elasticity means the ability to regain after the removal of deforming force. Now, if I ask you the reverse question, that which of the two can withstand greater force, the wire or the rubber band? The steel wire or the rubber band, which can withstand greater force?
Steel wire.
So let's say if I apply 1000 Newton on the steel wire, or maybe 1000 Newton, maybe that's too much. Let's say 100 Newton on the steel wire and 100 Newton on the rubber band. What will happen? The
Yes,
rubber
in
band will
steel wire there will be deformation, but in rubber band it will retain its original shape.
in rubber band it will
Retain its original shape because it's elastic.
rubber band. Okay. So it is the other way around from your intuitive idea that the steel wire will get deformed, and once you remove the 100 Newton force, it will regain the original dimension. So it will never get permanently deformed. Whereas in case of rubber band, it will deform very quickly with even a smaller force. Let's say even if you apply the 2 Newton, it will deform a lot. In fact, it will never be able to withstand that much force at first place. So maybe around 5 Newton it will break. So the idea is not about how much it elongates. The deformation or the elasticity has nothing to do with the elongation. It has to do with that what greater force you can withstand and still recover. So the whole idea of elasticity is that what is the biggest force I can apply, and still if I remove that biggest force, you should be able to recover. So now the extent of force which we can apply And upon removal of that force, if the body is able to regain the original shape, size, and dimension, then we say it is having the greater elasticity. So the greater elasticity has nothing to do with the amount of deformation. In fact, something which can deform very easily are poorly elastic because they don't have the resilience. They get deformed very easily. So at first place, the elasticity, as you understand, and the elasticity as we should understand in terms of physics, is quite different. So in physics, something which can withstand greater extent of force and being able to recover its dimension once it is removed will determine the ability of elasticity or extent of elasticity. It is not about up to what extent you're deforming it. So the amount of deformation is actually not the parameter to judge the elasticity. And it is quite, you can say, counterintuitive for most of you to understand this definition. So the definition which you perceived so far is totally wrong. So we have to understand in a different context. So now elasticity
So
is the force.
deform here means like you cannot regain its original shape, right?
Deformation is, the length of deformation is simply the dimensional changes. So if you can bring a big change, then that is
And
not the guarantee of
yeah,
elasticity.
and while deforming, if you go beyond the elastic region, you enter the plastic region, right? And it like rubber
Correct.
band snaps and break.
Yeah. So even these rubber bands are very prone to deformation, permanent deformation. So if you stretch by a long value, in fact, it will never recover also.
Yeah, it becomes
Then
plastic.
very bad. Yeah, it becomes very quickly plastic. But it is not true for the steel bar. It can withstand the even bigger force and still being able to come back to the same dimension. So in elasticity, what exactly we study? So we study two things. One is called the pressure, and other is called the stress. So we'll quickly revise what is pressure in case of solid bodies. So pressure is the external feature. You can say that. So if we have a surface and if you apply some external force, then this force will have two components. And always remember that pressure in case of a gaseous system or a fluid system is different from the pressure in case of solid bodies. So the actual force is the red one. Let's call it F. This is theta. And the horizontal force is F cos theta. And the vertical is F sin theta. So now the question is the pressure is defined by the force which is normal to the surface, and it is always external in nature. So we define pressure as the normal force upon area. A is the area of the surface. And this is definitely equals to F sin theta upon A. So if we want to define what is pressure, we can say it's a external force acting normal to the surface per unit area. So in case of gas and liquid, the pressure is nothing but the ability to transfer the momentum by the the chaotic or thermally excited molecules. So that is the difference from what we learned here. Just so the definition of pressure in gases are quite different. I mean, of course, it is also defined as the force upon area, but the cause of pressure there is the momentum transfer by the individual gases or liquid molecule. In case of solid, the pressure is simply the external force applied on the normal to the surface per unit area. So that's what we call pressure. So pressure is something that we build on a body by applying externally. Okay. So now every pressure, let's say if you apply pressure on a body, what will happen? So if you apply pressure on the body, it means if you apply some force on the body, it will deform the body. So a body will undergo some sort of deformation. So as a result of deformation, let's say if you start, I mean, if you take any object and if you start compressing, maybe you can take a rubber ball or you start pressing it. So can you press indefinitely or will it stop after some time? The
Stop.
pressing will. So how much you can press depends on how much force you can apply. So normally with your bare hand, you can apply certain force, and you must have experienced that it cannot be pressed indefinitely. It stops after some time. So the question is why it stops deforming after some time? Like what exactly stops it? Okay. So that's the question that we need to ask ourselves. That what exactly stops the body? So you apply force, then the first thing is it gets deformed. But does it get deformed forever, or if it is stopped, then what stops it? So the answer is everybody when gets deformed, it develops something internally, some sort of opposition internally within the body. And this internal force we call a restoring force. The restoring force is something invisible internal force which you don't see, which is like a response to your force. So after a certain limit, the restoring force exactly balances out your force. But the problem with the restoring force is it always develops in proportion to the amount of deformation. It means when you apply a 10 Newton force, let's say in the very beginning the restoring force will be 0. Now, the moment you deform a bit, it may become 2 Newton. If you deform further, it becomes 4 Newton. If you deform further, it becomes 6 Newton. If you deform further, it will become 8 Newton. If you deform further, it will become 10 Newton. Now, because 10 is exactly equals to what you apply, it will never let you deform more than that. Now, when you make it 12 Newton, then it has to deform further to again balance the extra 2 Newton. Again, if you apply 40 Newton, it will also try to increase the value to 40. In the due process of deformation, sometimes body will lose the property of elasticity. So it may break down, it may snap, it may tear apart because the internal structure of the molecules or atoms they provide the elasticity. So microscopically, it is the atom and their rearrangement which provides the elasticity. Sometimes what happens, like you deform to an extent that the atom fail to realign. So at some very microscopic level, things are just getting deformed. So sometimes the atoms and their attraction that is getting lost. So depending on the, of course, the if you talk about the polymers having the cross-linking structure, which gives them the extra ability to deform. But in case of metallic crystals, they don't have such things. So metallic crystals will have the atoms at the lattice point and the free electrons in the vicinity. And this crystalline is structure is like a very three-dimensional mesh grid. You can think like a 3D mesh grid. And also in case of crystalline object, or mostly I'm mentioning metals, the two lattice points are very close to each other, which generates the attraction power. And these mesh grids are so rigidly fixed that the extent of deformation is very small. So you cannot deform indefinitely or by large value. But it does not mean that they cannot withstand the greater force. In a return, they do not deform easily. It means they have the very high resistance. So you can apply a very large force and still the crystalline shape will maintain its you can say structure. It may get kind of tilted. So you may think of a cube which is getting tilted by space, becomes parallel piped in shape. So a crystalline body like metals, when you apply some force, large extent, so first of all they will try to just change the dimension of their lattice separation, and this lattice separation will change by very small quantity beyond your imagination. It may be nanometer or maybe uh, picometer, maybe less than that also. So now the change happens at a very small scale, and because of the large number of atoms in a chain or in a length of the object, the overall change which you see is the sum of the changes which happens at a atomic level. So definitely a larger body will show you a significant change, and a smaller body will show you very insignificant change, because the change is happening at atomic level, and for every two atoms, if the separation will grow, as a whole, the net change will be really big to be observed. So in case of polymers, which are like organic compounds mostly, so they have a very different structure. So they have the cross links. In fact, you can bend them, and the atoms can be really go really far. And for atoms going really far, things will be in a way that it will show you a large extent of deformation. And of course, for that reason, we use the polymers for various purpose. So if you have to, I mean, create a bungee jumping rope, of course, I will not use a steel wire. So what I will use is the rubber wire, rubber rope. You can say the rope is designed in such a way that it can deform to a great extent, and we make sure that the extent the deformation is so large that it takes time to deform fully. And by increasing the time, we decrease the impact. If you remember, the impulse is the force into time. So if I increase the delta t, f will decrease, right? So you will not feel a large value of jerk. So we know that if you are moving with a velocity v, you have the momentum mv. To stop, I need to create the impulse of mv, right?
Yes, sir.
mv now mv equals to f delta t. So I must increase the time interval to decrease the force on the person who is, I mean, having this rope attached. And that is the whole idea of the using the elastic ropes, which can deform to a great extent, and thereby it will decrease the impact. So that is the crucial part of deformation. In a way, it is of use to us. But of course, we do not want the bridges to be elastic like a bungee jumping rope. So if the car is moving, they should not deform a lot. So of course, for the infrastructure, we want rigid structure, and even these rigid structures, because they are so giant in dimension that their deformation can be significant. And because the deformation can be significant, so we must take care of the deformation of the giant structures because their weight, their load is really high, and they are very prone to deformation because of the extreme load. So they are in tons and tons and tons. It's not like in kgs. So the gravitational force is really large, and to withstand that much force, this material undergoes deformation. And so the designing of the any building or bridges or any infrastructure, the elasticity is the first thing that is studied. So whatever material that we is used in the building creation, it undergoes a lab testing, and everything about the material is studied, whether it will bear this load or not, and everything else. So that is true for the everything else. So the manufacture of the goods, like which makes the iron rod and all, they adhere to the specification by the researcher, and then the construction starts. Okay. So elasticity is a very integral part of construction, you can say, in general. Without this, we cannot think of construction. And the study of material is an extensive job. So you can imagine that if NASA has to use some specialized material to build the rockets, they need to do advanced metallurgical research, and these study the properties of elasticity and everything else before they create the you can say the product, whatever they want to make it. So we need to study elasticity for various reasons. It's not just about solving question, but we also need to study elasticity for the reason that if you want to go into the field of civil engineering or maybe mechanical, then the elasticity will be the one of the biggest component of learning. So for JE, we study as a very small piece of information. It's like just basic nuance of elasticity is introduced here, but later on the elasticity itself becomes the book, you can say. This itself is a complete chapter. And of course, elasticity will come along with the mechanics to actually make some sense. So now, depending on the different internal structure of a body, whether if we talk about the metal or if we talk about the polymers, the deformation amount will vary. But elasticity should not be determined by the extent of deformation, rather by the ability to withstand greater force and still being able to come back once it is removed. That is the elasticity. So if something can easily get deformed, it means its withstanding power is very poor. So of course we'll put into the category of poor elastic. Okay. So now something which cannot deform, something which cannot restore itself is called plastic. Now again the plastic or plasticity has nothing to do with the the organic plastic, the polythene or polyethylene or whatever polymer you have heard, PVC. So plastic, the word which we use in day-to-day life, has nothing to do with the word plasticity and plastic in physics. So plasticity or plastic means something which cannot regain the original shape and size, okay, once you remove the force. So for example, you can take an example from mud. If you deform a mud will never restore back. So it will get deformed permanently. Okay. So in case of plasticity, it is the inability to regain the original shape, size, and dimension. So it is the inability. So it means something which is plastic will never ever regain. It will be happy with the deformation which you have brought. Understood? So you can also study plasticity as a reverse in or inverse process of elasticity. So if you can say if elasticity is more, so we can say plasticity is less. And something which is perfectly elastic is having, you can say, zero plastic or very poor plastic. So please do not bring the rubber band and the plastic of your daily life into the physics, because they have nothing to do with the physics. Okay. So let's define the stress now. The symbol is sigma. And what is stress? It is also like a pressure only, but the difference between the pressure and the stress is that pressure is always external, but the stress is due to the internal forces. So how we define it?
Sir, I have one question.
Yes.
Sir, any material which is hard to deform but will not regain its original shape will be considered in plastic, right?
I will consider as plastic. So you can take the example of diamond. So diamond is very hard. In fact, the hardest. Okay. But it is not at all elastic. So it's brittle. So it can withstand the greater extent of force, but a slightest you can say agitation in the atomic structure will break the entire object into parts. So brittleness is like you may withstand the force, but you cannot deform at all. It means any deformation will just break you. So that's a
Okay.
different. So it is defined as the internal restoring force So you can think this way that let's say if you are studying in science academy and we give a lot of homework, so your parent will say that our kids are having tremendous pressure of doing the homework. And when you actually try to do the homework, then you develop stress. So stress is something developed internally. So you develop internally, and it is the consequence of pressure, right? So if you don't give any homework and if the life is so chill out, then of course you will not develop the stress. So the pressure is the, you can say, the cause, and the stress is the consequence or the effect. And the problem with the stress is it is always in a kind of a growth grows proportion to the deformation. So stress cannot be developed at once. It develops gradually. Okay. Pressure is like the you apply force. So when you apply force, then pressure is already created. But once you create the pressure, the stress is not the instantaneous value. So stress will be a delayed response. It will first deform a bit, and once the deformation has gone to certain extent, then the force will be equaling or balancing out your pressure. So stress is a delayed response. Pressure is the instantaneous response or effect which you create, and therefore we need to understand that stress is not the pressure, although at equilibrium they may balance out each other. So pressure is pressure, stress may or may not be equal to pressure. So in various situations, the stress will vary than the pressure. Okay. But in many other situations, the stress and the pressure is going to be same. So that is what we need to understand.
So it will grow to a finite value, stress, or
yes, stress will only develop up to the certain value, not it will develop forever. So if you have the fixed force on a body, then stress can only go to up to certain extent. So we'll see that as a numerical. But stress is not same as the pressure. Okay. So now, in case of pressure, what we learned that it is the normal force acting per unit area, but that definition is not true for the stress. So stress can be defined in more complex form also. So let's say this is the body, and this is the imaginary cross section which I have drawn. So you should not take this as some sort of cut. This is just a cross section. So imagine that you apply force on this surface. Let's say you apply force F from both sides. Now what do you expect? The body will move or will remain at rest?
Will remain at rest.
Correct. So body will remain at rest for sure. Okay. So if the body will remain at rest, then if I choose any random cross section, what will happen? If I choose any random cross section, then that cross section will develop some force, isn't it? So for the sake of understanding, let's say this is theta angle, and let's say this is the random cross section taken to analyze the stress part. So what we can do is we can just take this separately. Okay. I need to do it. So this is the ABD. Okay, we are drawing it separately. It doesn't mean I have cut. So what we can see that the applied force is F, and how much force you expect acting on this surface. So if I name this as part 1 and part 2, so how much force is applied on the part 1 due to part 2? So what do you expect? So the body is at rest, right? So any body, if you take even a part of it that is also at rest, it means every part will have the net force 0, correct?
Yes.
Now because every part is having net force 0, and if I know one of the answer, let's say if I know the answer from the left, so this part is experiencing force F from the left, then to keep it at rest, how much force we must apply from the right?
F.
And what should be the direction? Like this or like horizontal? Hmm? Normal to the surface or at this angle, like horizontal to surface, like this or like this? Tell me.
Sir, are these two separate? Yes.
Pardon?
Sir, these two are separate parts and they are just joined together.
No, these are joined. This is only one part. I have just imagine one cross section, random cross section in the body. Now this is like a cuboid. You can think of this is three-dimensional cuboid.
Sir, sir, the force will be means in the opposite direction to the F.
So this is the cross-sectional part, which I have just considered internal part. Yeah, what did you say? The force will be
Opposite.
opposite. Yeah, that's correct. So force is bound to be opposite. There is no option. Then for the net force to be zero, the only option is the applied force must be, I mean, the internal force developed. Now, the blue arrow is representing that what internal force is developed and acting on this imaginary surface. So on this imaginary surface, the right body will apply force on the left, and on the same surface, the left will apply force on the right. So the whole idea of internal forces, now you can see that this is the applied force. And this is the internally developed, or you can say internal restraint force. And you can clearly see that they are equal in this particular case. So luckily, the internal restoring force is exactly equals to the applied force, even for any random cross section taken. If I call this area as A, what will be this area? Can you tell me this area? A dash. A dash is the slant area.
So on the right, at sin theta.
Sure, please will you in the screen, previous screen. Done, sir.
So it is defined as the, okay, now this is the internal force. Now what we're going to define is the types of stress. So what I said that the pressure is defined by the normal force upon area. And we have just only one, we don't have types of pressure, we just say pressure. In case of stress, because it is the internal force and it is subjected to the like internal action reaction pair, this will have two types. So unlike pressure, the stress will have types. And the first is called normal stress, which is quite similar to the pressure definition. And we define by the symbol sigma n for normal. And the normal stress is defined as the restoring force normal component to the surface which you have taken upon area of that surface. But at the same time, we do have something called the tangential stress. And how we define? But obviously, the definition is if restoring tangential to surface, or you can say parallel to surface. So stress is always of two types. One is parallel to surface, another is normal to the surface. So depending on what surface you consider, you can have tangential as well as uh, normal stress. Okay, so this is quite possible, but this is not possible for the pressure. So we don't define the tangential pressure and the normal pressure. We have just only one pressure. My pressure is only normal. So externally we have only normal pressure. Okay. So now for the given scenario that we were discussing, if we choose the random surface, I'm taking the tilted surface, and if the applied force on the body from the left and right are equal, and if I consider only one part of it, so we can also we have realized in fact that the internal force will be on the one will be like this and two will be on the right side. So I'm just taking the one part, the part one. And luckily, because of the condition of equilibrium, we got the answer. This is also F. This is theta. This is also theta. So if I draw the normal to this point, so this force will have a component. So this force will have component in this direction. This is how much? F perpendicular, and will have component like this. Can you tell me what is the F perpendicular?
F sin theta.
Correct. Now what is F parallel?
F cos theta.
Now this F are applied force of the internal force.
Internal force.
Correct. So first thing you need to remember that in the FBD, the F must be internal. It cannot be external force. So when we solve the question of stress, we only consider the force which we can see what is developing there by drawing the FBD. So you cannot get the internal force unless you do not draw the FBD. And to know the internal force at a given cross section, you must draw the separate ABD for the part of the body which can open that surface to the or expose that surface to the viewer. It means I will just do the half of it the way I did in the previous page, like this. So always to know the internal force at a given cross section, you must cut from there and then draw the ABD. Okay, let's say how we find the internal force on a spherical shell of some thickness. I want to know the stress here, so I have to cut something like this. And once you cut it, you can see this is a some patch like this, and then we have got. Now you have to expose this part to the viewer, then only you can think of the calculation of stress. So there is a thumb rule to find the internal force. You have to cut the body. Now cutting can take place in some more informative manner. Like if we know that if I cut like this, I can do the calculation easily. So we'll do that. So generally we cut the object into symmetrical fashion if possible. Let's say if you have a sphere, if you have a cylinder, I'll cut in two halves. for the sake of calculation of internal forces. And if it is some sort of irregular object, then of course we will not get questions on those objects because things will be difficult. So to find the internal force, we have a thumb rule. And what is the rule? You must cut the body at the desired cross section if it is mentioned. If the only question is find the internal force, I mean, if they don't explicitly mention the cross section, then your job is to cut into two symmetrical halves and then draw the ABD of any half to get the internal force. Is this clear? Is this clear?
Yes, sir.
Yes.
Okay. So now we have the two forces available to us, and we know if this area was given as A, we got this area of this cross section A dash. What was A dash?
A by sine theta.
So now if I ask you what is the normal stress developed there? Normal stress.
F sine square theta by M.
Hmm? So it will be F perpendicular upon A dash. That's it. And
Theta cos theta by M.
so we can add F sine 2 theta by 2 in short. Hmm?
Yes.
Now the normal stress can be of two types. It may be tensile or it may be compressive. So tensile means you pull the surface. Compressive means you press the surface. So when we go to buy the cement, if you look at the advertisement of cement by various cement company, let's say Ultratech is the biggest cement company in the country, in fact in the Asia. So now how they advertise, they say Birla cement, Ambuja cement with a great compressive strength. Because the cement structures are basically buildings and they have to bear the load. Now cement is most suitable for load bearing, or in a way you can say the cement can bear the compression much easily. But they are not good with the sideways push. They are not good with the pull part or tangential forces. So they can only bear the load. And therefore, in the construction, we never use pure cement. We attach some iron rods as called the RCC, the reinforced concrete cement. So first we create the iron mesh, which you must have seen during the construction of, let's say in Mumbai, you can see metros and you can see everywhere else. And we put the first iron rod and then we put the cement around it. Okay. So we are trying to derive the two different properties. One is the loading property, which is given by the cement. But for any sideways movement, the cement can be broken easily. So to support the some sideways push or maybe some earthquake, the iron rod will hold it sideways. It means the tangential part is taken care by the, or you can say the sideways movement is taken care by the iron rods. So they are very much prone to they can undergo any sort of deformation. Uh, but the iron rods are not good with the load bearing because they can deform easily. Okay. So for the load bearing, the iron bars are used in many buildings, but that is called the route iron. I mean, that iron is very hard because it is mixed with the carbon. Okay. So when you add carbon to the iron, it becomes really hard. It loses the elasticity. And why it loses elasticity? So when you add carbon to the iron, it loses the elasticity. If I ask you why, can I explain? And if you add too much carbon, then the iron becomes brittle. So as I said, iron is a metal, so it will have the crystalline shape and it will have some interstitial spacing. So what carbon does is that carbon is a very small element and it exactly fits the interstitial gap. And when you fit the gap, you restrict the movement of iron atoms in a way you will not allow to deform easily. That is the reason why we add carbon to give some rigidity to the iron. So the soft iron, that's why we call the pure iron as soft iron because it is easily able to bend itself. So when we create the utensils, we add carbon and to resistance to for the rusting we add chromium and some other metal, and then we design the stainless steel. So the stainless steel is not steel; it is an alloy actually. So steel is pure; it's just iron. And to make alloys, you can add some other metals and non-metals as well. Okay. So carbon is by virtue of the size, it easily fits the interstitial gap of iron crystal and thereby reducing the movement and hence the elasticity, but it adds up the rigidity. So it becomes more rigid but poor elastic. And that is why we use the soft iron to create the electromagnets. Okay, the steel. Because electromagnets needs to be okay, we'll talk about the magnetism and the iron and magnetism having the very old relationship. So we'll talk about in detail in chapter of magnetism. And we do have to study the magnetic properties of material and the electromagnet and the permanent magnets having the different construction from the same iron. We use pure and impure for the same reason as I discussed. So the stress can be tensile and can be compressive. Now tangential stress is very common. Let's say if you apply the face cream on your face, so generally your movement of the hand will be tangential to the surface, but at the same time you also press the surface. So by pressing the surface, you create the normal stress, and by moving your hand tangentially, you create the tangential stress to the surface. Not only that, you can apply the same concept in while when someone is shaving. So they take the razor and they press it gently to create the normal stress, and then they pull it tangentially, which creates the tangential stress on the skin. So as the blades are having the sharp edges, it cuts through the hair part and leaves the skin there only. So if we talk about the peeling of a potato using the peeler, the same thing happens. You press the peeler, create the normal stress, then you pull it tangentially, you create the tangential stress, but because of the sharp edge, the peel gets peeled off of the object. So in our day-to-day life, we always apply the normal and the tensile stress without realizing. So we always press something and we pull tangentially to create this stress. Now, liquid do not bear the tangential stress. In liquid, we don't have the tangential forces possible. And because of this property, they can only withstand the normal stress, but not the any sort of tangential. So in the Pascal's law, we study about the pressure because liquid is good with the compression. So you can compress the liquid and it will create the pressure. And that pressure is which we create by applying some force on the liquid. That force will, that pressure will, which we develop, will get transmitted throughout the volume. So liquid is a very good medium, you can say, which can transfer the pressure which you develop externally, and it can act as a kind of communication. So with the help of this pressure wave, the whales or the dolphins or any aquatic creature, they communicate miles away because the speed of sound, which is nothing but the pressure wave, travels at a speed of roughly 1.5 kilometer per second. So in 1 minute you travel how much? Roughly 90 kilometers, right? So traveling 90 kilometer in roughly 1 minute, you can easily communicate someone at a distance of hundreds or thousands of kilometers away in few minutes at least. And that is how every aquatic creature they communicate. And because of their dimension, they create different amplitude of pressure waves, so they know exactly who has created. Yeah, sometimes miscommunication may happen because of the some unseen circumstance may create a similar wave pattern. So when there is a tsunami or when there is some volcano eruption within deep inside the ocean, the creature will come to know about that very soon than anybody else, and then they start behaving differently. So you can also observe the behavior of the fish or the whales or the other aquatic animals to guess about the tsunami which is coming your way. So there are various things. Of course, they have the ability to understand the pressure wave. And dolphins create the ultrasonic wave, which is a very nice way to communicate very effectively. So see how interestingly they communicate within the water, thanks to the normal stress that we can develop in the water, and then the stress is sooner transferred to the next layer of water because water is almost incompressible, or you can say the water will have the infinite elasticity, close to infinite elasticity when it comes to the pressure or pressure wave. So again, the wave transmission has to do with the elasticity only because we disturb the air particle. Let's say when I'm speaking or when you guys speak, we create the air pressure wave, and because the air is also having some sort of elasticity which you don't realize. So even air wants to remain in certain density. So if you compress the air, you increase the density and therefore you enforce the elastic behavior of air also. And if you want to understand the elastic behavior of air, you can fill the balloon with air and you can compress it and you can feel the okay, it is having the elastic behavior, correct? So
Yeah.
everything, it's a liquid or it's a gas, everything having the elastic behavior. The only thing is the way we understand that elastic behavior is different. So for solid we behave, I mean we understand easily, but the elastic property of liquid and gases are somewhat complex. And once you understand the elastic property of the liquid and gas, it's very easy to understand the wave motion. So what we call wave is nothing but the creation of pressure and its transmission to the next layer. That's called wave. So wave is basically we call the propagation of anything, any disturbance which you create in a medium, which can carry the energy and momentum, we call wave. So every wave which you know, whether it's transverse or longitudinal, the transverse is different, but every longitudinal wave is a pressure wave. Okay. And therefore, every longitudinal wave demands or needs some sort of elastic property. It means a medium with no elasticity cannot have longitudinal wave. And because there is no medium without any elasticity, it means every medium will have some elasticity. Therefore, every medium can have longitudinal wave. A medium can have longitudinal wave. So in a vacuum, we cannot have longitudinal wave. Why? Because in a vacuum, we don't have medium, so there is no concept of elasticity. And because there is no concept of elasticity in a vacuum, so we don't define the longitudinal wave. So in a vacuum, what we define is only the transverse electromagnetic wave in some sense. Okay. So that's why the chapter called the wave and sound, basically the wave motion, has to do a lot with elasticity, and that's why we'll restrict and that chapter. We'll study that chapter only after we are done with the elasticity. So after the stress, the next topic is what? Deformation. Correct. So for example, we can just do something. So for normal stress, if you just pull the surface perpendicularly, it will create the tensile. But in the bottom case, what we have?
Compressive.
Compressive. So when you go and so when you observe the advertisement of link locks, what they say? Link locks will with very high tensile stress, because to break the lock, you will pull the handle, right? The round bar. And when you're pulling something, you're trying to create the tensile stress. So the link lock will come with tensile stress. In the keyword which they use in the advertisement is tensile. For cement ads, you will hear the word compressive, and that's very common. Now the tangential stress is also having the other name called shearing stress. So to remove the wool from the sheep or the yoke, what we use from the shear machine. So it creates a tangential force. Okay. So after the stress, the next concept is called strain, or the amount of deformation. Symbol is epsilon. So what is strain? So we have discussed that when you apply some force, the body will get deformed. Now we also need to realize that a bigger the body, bigger the deformation, or you can say greater than deformation. So it is a very common experience that deformation is always found to be in proportion to the actual dimension. It means a bigger object can undergo a bigger deformation, and that's very simple to understand. If I give you a bamboo stick, a long bamboo stick, you can bend it. You can create a bow shape. But if I decrease the length of the bamboo stick, what will happen? The bending will become more difficult.
Yes.
And let's say if I give you just 1 inch of bamboo stick, can you bend it at all?
No, sir.
No. It means, but you don't realize that the amount which you bend the small stick or the big stick are same. So if I cut the every part in a big bamboo stick, if you look at small pieces, are they bending much? The answer is no. They look almost straight, isn't it?
Yeah.
So even let's say if you make a shape like this, but if you only consider the small part, is it bending much? No, 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 no. But as a whole, yes. The thing is, deformation is a local phenomena, and it happens over the length of the object. And what you see is the overall deformation. You don't see the individual deformation. Understood? So, okay, what is epsilon? Epsilon is the Greek symbol.
That is epsilon of E.
Pardon?
So I'm
So that is epsilon or
yes.
E.
This is epsilon, not E. You write C and then cut it.
But
The same symbol which you use in belongs to. You know, A belongs to set A, no?
Yes, sir.
So you call belongs to in set theory. This is the epsilon. In electrostatics, we use epsilon naught, epsilon R, epsilon. In different contexts, it will have different meaning. But this is the Greek symbol epsilon. Epsilon, no, you can say it. So the now it is obvious that a bigger body will undergo a bigger deformation. So deformation is always proportional to original dimension for a given force, of course. Like if I make a, if I fix the force, then these two will vary in proportion. So we wanted to define something which is independent of the dimension, and that the only way is to take the ratio, right? So deformation, if it is proportional to original dimension, so deformation upon original dimension will be a constant property for a given force, correct? And that's why we define the strain in this particular fashion. So the strain itself is defined as changing dimension upon original dimension. So if you talk about the rubber band example, it will have very large strain. But if you talk about the steel bar, then it will have very small strain, correct? Because the dimensional
yeah.
changes are not very significant. If you apply the same force, so if I take the steel bar and one is the rubber band, if I attach the same load both here and here, This will go to this greater extent deformation, and this will even just move by
DL.
that's it, some fraction of millimeter. So this may be millimeter. That's why, because the deformation the steel wire is very small, we use the vernier caliper to measure it, because vernier caliper can measure 1/10 of a millimeter. Correct?
Yes, sir. Least count is 0.1 mm.
Yes. So we have to use that vernier caliper as a measurement or measuring tool in case of steel wire. In case of rubber wire, you can just take a ruler and measure it. It's too big. So the strain wise, which is undergoing smaller strain, steel wire, but the load on both of them is same, na? mg. So you can see the applied force is same, but to balance the applied force, the rod, this sorry, the steel wire will deform a bit, and this much deformation is sufficient to balance the block. But when you hang the block from the elastic object like a rubber wire or a spring, you can say it's like a spring only, then it undergoes a greater deformation before it is balanced out. So definitely the delta L and the delta L in this case, this is much bigger than delta L, correct? So when we talk about the strain is only the ratio. And why we are defining as a ratio? For the obvious reason. Because ratios will not depend on the dimension. So it is something like a very much a property. So now this is the simple definition of strain. It's not a big deal. So now we can talk about varieties of strain. So you can just put in the word definition is what? It is defined as the ratio of changing dimension upon original dimension upon the application of deforming force. So this mg is what? And this mg?
The
This is registering force. So that is developed inside the body. So the behavior is similar to the spring force as you have studied in laws of motion. Now we'll see the types of strain.
tension.
Yeah, tension force developed is also internal registering force only. So tension and strain is internal force, internal registering force. The types of strain. So how many types of strain we have? So we have two types of strain. The first is called another is called this is also called lateral strain. So let's take a chewing gum and stretch it. Don't do this, but imagine. Or take some like rubber band with some strip uh, shape And if you pull it, what you can see that the length will elongate, but the width will shrink, right?
Yes, sir.
Yes.
So are you shrinking the width or you're pulling the strip? What you do?
Pulling the strip.
So it means you're not trying to shrink the width, right?
Yes, sir.
But it is happening. So in every body, if you have a body, so when you apply force, one dimension is elongated, the another dimension is shrinked actually. And this is not what we are doing intentionally, it is happening. Correct? So we are not trying to do this. So this is how you are applying the force. Now the length, if I say is L, and if I say the diameter as D, then the new length we can say L plus delta L, and the new diameter is D plus delta D. You may ask why say plus, why not minus? The delta D itself is negative. Don't worry. Okay. So we are adding something negative. It's okay.
Yes.
So the longitudinal strain is defined as the strain developed along the applied force. So where you applied the force, the direction in which you have applied the force, the deformation in that direction is called longitudinal or parallel. The meaning is parallel to applied force. Now what is transverse? The deformation which happens normal to the applied force at right angle. So that's why what the transverse means, at right angle. Understood? So the transverse strain or the lateral strain is the strain which is happening in the direction normal to the applied force at right angle to the applied force. It is clear?
Can you repeat again?
So longitudinal strain variety is epsilon L and transverse variety is epsilon T. So the longitudinal means along the force, not the length. If I'm applying the force in towards right and left, so any deformation along the force we call longitudinal. So any deformation along oblique parallel to applied force is called longitudinal. So what is transverse? Any deformation. And therefore the longitudinal strain we can write as delta L by L. But how to write transverse? Minus delta D by D, because the strain is always a positive quantity, and as I said delta D itself is negative, so we put a minus and before it to make it positive, because strain cannot be negative. Okay, but are these two only two types of strain? The answer is no. We have third type, but because its definition is quite different from the first two, so I will put it as a third category above, or maybe on the next page. So I will put here to be continued. So let's see the other type of strain, which are equally famous, but their definitions are very much different from what we have learned. So we'll try to understand in this context. Another strain, the other strain that we develop here, you can see that the objects will have a dimension. So it is having some length and some area of cross section. So you can check the change in length and you can check the change in delta D. So mostly for three-dimensional object, or you can say three-dimensional finite shaped object, or with some known geometry, we may define longitudinal, we may define transverse. But what about the body of irregular shape, where the length is not defined, when the width is not defined, when the radius is not defined? It is neither sphere, it's just a random shape object. So you go to some beach and you just pick some stone from the beach of any random shape. Then we cannot define the longitudinal or transverse in such case. So for three-dimensional irregular object, the only way to define is something called volumetric strain, which is of course a part of anything. It could be uh, lateral, it could be longitudinal. It is something, but mostly it is longitudinal also. But because the way we define is for any shape body, the body of any shape need not to be linear or some finite shape. So the definition is called volumetric strain. And the benefit of volumetric strain is it only directly look at the volume to understand the strain part. It will never look at the length or the width. It will just look at the volume. And it is very essential for the strain develop in liquid or gases. So let's say when I'm saying something, then I'm compressing the air, and thereby I'm creating the local strain in the air. And the strain that we develop in air is definitely volumetric strain, because you cannot see the length of air or width of air. Similarly, in liquids, when some disturbance is created, it also creates a volumetric strain. So in case of fluid, the only strain we talk about is volumetric. We cannot talk about the longitudinal or transverse. Okay. In case of solid body, we talk about the longitudinal or uh, transverse. But in case of liquid and gas, the only thing we talk about is volumetric. Now the question is that can we talk about volumetric in case of solid also? The answer is yes. Volumetric is for liquid and solid everything. But the other way around is not true. So we cannot define the longitudinal for gases. We cannot define longitudinal strain for you can say liquids. The next is volumetric strain. We write as EV, and the last is called shear strain, which is again for a very different purpose. So when you are wearing a shoe or a slipper or a sandal, and when you walk, what you don't realize that you always push the ground backward. to walk forward. And therefore, at the bottom of the sole of the shoe or the sandal or the slipper, some tangential forces develop, and that tangential force will create some sort of torque, you know, as you know. So the tangential force always creates the sideways movement of the object, and this sideways movement is captured by the definition of shear strain. So the shear strain will attach epsilon s, and we'll study about this in a bit detail. So we'll go back to these two definitions, the longitudinal and transverse, because I want to define the third thing here only. So which one is intentional and which is unintentional here? You can see that longitudinal is intentional because the force is creating it, but transverse is developed out of nowhere, right? So we haven't put some effort to do that. But in order to preserve the volume of the object, they create the transverse naturally, isn't it?
Yes, sir.
So there must be some relationship between the two, and the relationship between the two we capture by a variable or a factor we call Poisson's ratio. You can say Poisson's ratio. Of
Yes,
course,
sir.
these are,
Transverse strain upon longitudinal strain.
yeah. So these are the French guys. We use a symbol mu, and the mu is defined as the unexpected upon expected. Okay, the ratio of what we don't want upon what we want. This is called lateral strain upon, and it is well documented in many situations. So for, let's say, steel wire, the Poisson ratio for various object of various shape, it is like a documented through experiment, and it is put as a table. So when you study the civil engineering in the first year of BTech, called elements of civil engineering, there you have to study about the Poisson ratio in detail. So you can add this definition as minus generally we write this ratio as a differential form. So I prefer writing this as dl by L. I prefer writing this as minus d by d, and so this becomes minus d upon d, dl upon L. And if we have a cylindrical object, so especially for this place is this. Okay, maybe putting here. So for a cylindrical object of radius r and length L, the diameter is twice of radius, so we can write the diameter ratio.
1/2.
So delta d by d is same as dr by r, because the d is 2r, so the differentiation will be 2 dr by 2r. 2 will cancel out. So when we take the ratio, it really doesn't matter whether we take diameter or the radius, right? So it is good to write as minus dr by r upon dl by L. Now a body is said to be ideal if its volume is conserved during the deformation process, but that is not the ideal case. Most of the body will suffer some volume changes also, and that's why we talk about the volumetric strain. So for ideal, let's say cylinder, volume is what? Constant. So let's say we have a cylinder of length here, so volume is pi r square. If volume is constant, so dV by V equals to the volumetric strain will be 0. If volume is constant, then the volumetric strain, which we will study later on, is 0. The dV by V is 0. And this will give you the answer that 2 dr by r plus dl by L, you know the difference is 0. And if you rearrange, what will you get? You get minus dr by r upon dl by L turns out to be 1 by 2, which is exactly the definition of Poisson ratio. It means the Poisson ratio is half for cylinder. So if something is ideal, it means if it does not undergo the volumetric strain or volume change, the Poisson ratio is found to be 1 by 2. For in any other case, it is always less than 1 by 2. So practically, the Poisson ratio is between 0 to half. So you just remember this, practically the mu is always from 0 to 1 by 2. This is the practical value of mu. Theoretically, we have different values. So I will talk about the theoretical value later on.
So why are you adding those values to 0?
Pardon?
Why are you adding these values to 0?
Why we are adding? Why we are adding to 0? Oh,
No, sir.
because
Why are you adding? Sorry.
what I'm adding?
So that 2 dr by r plus dl.
Okay, you know differentiation.
Yes.
You know product rule.
Acha, okay.
So if you apply the product rule, what you do? You differentiate the first thing, then you add and differentiate the other thing, right? So this is a shortcut
Yes,
of
understood.
differentiation. You take the power as a factor and you just write the fractional value. You know, this is how we differentiate. Okay, I will tell you this. Uh, we can do this practice here. So I hope you know this differentiation. If I have something A equals to, you might have done in the error part.
Sir, yes. Sir, I forgot that.
Okay.
Sir, I didn't see the ideal cylinder part. That's why.
Okay. Now it's clear.
Yes.
Now we'll come to, so this is the relation now. This page I kept only for the transverse and longitudinal because there was a third thing which is the Poisson ratio, which relates the two things. Now the volumetric strain, as the name says, is volumetric, so we can say define as. So by applying pressure or force, generally we tend to compress the body. We don't try to elongate the body. And by definition, we write as, because it is generally compression. Bodies can be compressed, but it's difficult to increase the volume of a body. So the volumetric strain turns out to be the change in volume upon original volume, you can say minus dV by V. So let's say you are the manufacturer of ball bearing. Okay. So you make the ball bearing, steel ball. Yes. But when you manufacture it, a company says that, okay, I have to use the ball bearing for some deep sea exploration. So if you use the ball bearing which is manufactured, and if you create the fitment in that way, the moment you go down the deep sea, and if the ball bearings are exposed to the water, the pressure will deform the ball bearing. So as you go deeper into the liquid, just you go deep into the liquid.
P0 plus rho GH.
So now it is manufactured at P0. So what is the extra pressure which you develop for this particular sphere?
Rho GH.
Rho GH only, because it was born at atmospheric pressure, correct? Just like we are born at atmospheric pressure. I'm ignoring the dimension of the ball compared to the height h. H is much bigger than h is much bigger than r, and so that we can treat this as a point, and we can assume the pressure same throughout the surface. So the extra pressure which we create is how much? Rho gh, correct? The additional, like the pressure at which it was manufactured and the pressure which it is experiencing right now, the extra pressure is rho gh, and that extra pressure needs to be further balanced by the body. So to balance this extra pressure, it will get deformed slightly. If you remember, I have told you in the very beginning that if something is like something is at equilibrium at one particular force, then if you change the force, then it will reshape itself in order to balance the additional force. Okay. So the deformation will be created within the sphere. It will get compressed, and if the radius is r, we can say that v equals to how much? 4 by 3 pi r cube. So the delta v upon v will be always equals to minus 3 times of dr by r. The power gets multiplied and we write fraction and ignore the any constant appearing in the formula. So this is the easy way to derive. So volumetric strain for sphere we can write as simply minus 3 dr by r, because for a spherical body the volume is directly related to the radius, correct? So similarly, if we have a cylindrical body, then how to add the volumetric strain?
2 dr minus 2 dr by r.
So for cylinder, we have written already. The volume is pi r square L. So we can say d. The volumetric strain will be 2 dr by r plus dl by L. We have written two terms
Plus
separately.
dl by r.
And something very interesting I will tell you. So this relation, if you remember something from the Poisson ratio, the dr by r we can write as mu dl by L, right? So the dr by r becomes minus 2 mu dl by L, correct? Plus dl by L,
Yes, sir.
and the dv by v we can also write as 1 minus 2 mu into dl by L. So for cylinder, the volumetric strain, if it is getting compressed, will be minus dv by v, which can write as minus 1 minus 2 mu. Of course, the length is negative quantities, that's why this is the negative sign. So these kind of manipulation you will face while solving numerical. We'll come to that also, don't worry. So this is the volumetric strain part. Okay. Now the last topic for the day is shear strain. So what
Sir, just one
exactly?
question.
Yes.
Sir, in the last page, we got mu is equal to 1 by 2. Sir, so that
That is what
mu
we
is
assume
less
that.
than equal to 1
Yeah,
by 2. No?
yeah, yeah. So now that there we assume that the volume is not changing, correct?
Yes. Sir, then the relation is less than equal to or only less than.
Yeah, mu is less than equals to half. Okay. So that's why this is negative. I mean, okay, what the way we should have written is minus 2 mu minus 1 if it is getting compressed. Okay. If mu is less than half, it will become how much? Negative 1. This will become negative 1. No? This is negative. So as a
Some is greater than
okay,
1.
no, I have missed this point. Here the minus will not come. We are elongating the rod as a virtue of elongation, the volume is decreasing. So you are pulling the rod, length is increasing, but the diameter is compressing or decreasing. As a whole, volume is decreasing. This is what we have to assume. So dl by L is positive, and the dv by V itself is minus of 2 mu minus 1. So you cannot like this,
So I didn't
or
understand this part.
pardon.
So I didn't understand this part.
Think this way. You're stretching the rod cylinder. The length will increase to L to L plus delta L, and the diameter will decrease from D to.
Entirely.
Okay. So now the delta V by V we cannot like this, no? Because the definition of the Poisson's is what? Minus dr by R is dl by L. The mu equals to
Yes.
this ratio. So from here, what we can write? The dr by R we can write as minus mu dl by L, correct?
Yes, sir. Yes, sir.
So if you substitute, we'll get this much minus. Okay.
Yes, sir.
So now 1 minus 2 mu, what I said is, I said that mu is practically something different from theoretical point of view. So practically 1 minus mu is from where to where? So if you multiply by 2 both sides, what you get? 0, 2 mu, 1. So 2 mu is less than 1. So here dv by v will be how much?
Positive.
Positive quantity. Which means here the volume will grow actually. If dv by v is positive, it means as the length will increase, the net volume will increase. So that's like something different. It is the property of the body. You're pulling the body by virtue which I'm not compressing it, I'm pulling it. So if you pull the rod, the volume may get extended. That's quite possible. In the previous case, in case of sphere, the water is pressing the sphere. Here the volume is decreasing. Like these are two different cases. One is compression, other is elongation. So if I put this into water, then this P will be like this into the plane, like this. Then dl by L will be negative or positive. Dl by L will be
Positive.
so this will be negative and dl by L, because if the length is if you compress it, it's like you have a
Acha,
formula. You
okay,
have to
compressing then negative.
compression negative, elongation positive is a different thing. So don't get confused. You just remember as a formula. In a context when we solve actual problem, then we have to think of we have to take positive or negative. So right now what we are writing is just a formula. Okay. So volumetric strain is what? Minus d by v. So the answer is minus 1 minus 2 mu. Just whatever the formula, just write down. Write down and leave this. Okay. The next is the shear strain. What is shear strain? So shear strain is the lateral movement of surfaces with respect to some other surfaces. So for example, if we take some body which is in the shape of a cuboid, and these are basically the mountings in a vehicle. Let's say if you want to put some heavy machinery, so they always have the base with the mounting of rubber. So we use thick rubber as a mounting. So your shoe will also have the mounting. So you can see at the back of the shoe we have some kind of mounting only, which you can say as sole. So now what is the role of the mounting? So imagine this as your shoe mounting. Okay. Now the bottom is like a fixed. I'm assuming the bottom is fixed. Just like when you walk, then the bottom is fixed. So what we do is we try to, let's say, apply a force like this. In our case, we apply force backward, but let's say you're applying force like this. And this force is tangential to the surface. As a result, what will happen? As a result, the top surface will move forward slightly. Correct? So the top of the surface will displace slightly, although it may be insignificant for you, but it actually displaces. So if I compare the bottom and the top, you can see there is a small displacement. Let's call it X. And the separation between the top and the bottom, let's call it L. Now for the sake of illustration, I must draw this bigger, else you will not get the idea. So now this is much easier to visualize. So the shear strain is defined as the relative displacement of two surfaces, two parallel surfaces, relative displacement of two parallel surfaces upon their separation. That's it. So you can look at the top surface and the bottom surface. Top is has gone x ahead, bottom is not going anywhere. So the relative displacement is x and their separation is L. So this is the definition of shear strain, x by L. But is that the only way to define? The answer is no. You can choose any surface here. That's called x dash. And from the bottom, let's say this is L dash. You can also write this as x dash upon L dash. Is this the only way to get the answers? The answer is again no. You take the top and the x dash, you can say x minus x dash upon L minus L dash. Even that is the relative displacement of the two surfaces upon their separation. Now, if in this way we can define in 1,000 ways, so the best way to define is by taking this angle as theta. And because when you take the angle theta, and these displacements are really small, as I said in the very beginning, we can think the theta as tan theta. And the tan theta is, this is nothing but the, correct? For a small angle, we just write tan theta as theta. And this gives the definition of shear strain. That shear strain is defined as only single variable theta. Understood? So we define, this is the way we define the shear strain. So how we define? the relative displacement between any two surfaces which you choose upon their separation. So we generally choose the surface whose displacements are known to us, and we divide by their separation, we get the shear strength. Is this clear? Hmm?
Yes, sir. Clear.
So this completes the stress and the strain definition, and we can see some more definition of strain. So for shear strain, I'll show you one more definition. So imagine if you have a hollow cylindrical jar. Okay. Imagine the point P here. Now, generally, when you try to open the lid of a jar, what you do is you press the jar lid by your finger or by hand, and then you try to rotate the jar, which is in turn creates the torque. So let's see the other perspective. When you try to tilt the jar as a whole get twisted a bit. So this is the point P comes to the point here somewhere P dash. So you are twisting the jar, you're opening the jar. So your hand is on the lid, but the entire jar is also getting twisted a bit, which you don't realize. And the point P comes to P dash. And this angle is really small, very small. Like let's say 5 times to 0. We don't see the much difference. So you can see the P has come to the P dash. Let's say the radius of this jar is R. So if I look at the top surface PP dash, so compared to the bottom, the top surface has moved by PP dash. So we can say the shear
R
strain
five.
equals to PP dash by L,
Yeah.
and PP dash is what, R5,
Fine.
correct? And this is exactly the theta. This theta is R5 by L. Because it's a very small, so we can write like this. These are very small dimensions. So for jar, we can always write the shear strain this way. Okay.
Sir, but phi is the angle, right? Then
Pardon?
theta. Oh, okay. No, theta is phi.
Theta is very small, so you can write like this. So next we'll start the Searle's experiment. And before that, I will request all of you to go and revise the vernier caliper in great detail, because most of the question in error part in JE Advanced will be based on the Searle's method. So all question of vernier caliper, whichever you have seen in the JE, they always based on the Searle's experiment, which is the next topic we are going to discuss. Okay. All right. So I'll end the lecture here only. We'll start the Searle's method in the next lecture.